Hello everyone, this video is about finding the pH or concentration of hydronium ion for a weak acid and also how to find the percent ionization of the weak acid at the same time when the initial concentration is given. So for doing so, you have to first distinguish between a strong acid and a weak acid. So a strong acid, as you can see up here, is an acid that ionizes completely. It ionizes 100%. So right away, you can find the concentration of its ions by dissociating it. However, for a weak acid, because it only ionizes partially, you have to construct and first of all make an equilibrium sign and then construct an ice table in order to find the concentration of its ions, because it's not going to be 100% and you have to do some work to basically find those concentrations. So in this example, I've given you 1 molar CH3COOH, which is a weak acid. So because of that, I know the equation is going to be at equilibrium. So what I can do is I can put this weak acid in water. You can also not put it in water if you don't want to, but if you put it in water, it's going to behave like Bronsted-Lowry acid and base. So in this case, water is going to be amphiprotic because that means it can be both an acid and a base. But the weak acid is just an acid. So because water is coming with an acid, in this case, it's going to behave like a base. So what happens is that based on Bronsted-Lowry definition, the acid will give away its H plus or proton to water. So it would become CH3COO negative, and then H2O will receive the proton. So it will end up being H3O positive, which is the hydronium ion. So the way I wrote it is based on Bronsted-Lowry definition. I could do this. I had this option too, to write the equation this way, basically based on Arrhenius definition. So just show how it produces H plus ion in the solution. So the the base would end up being CH3COO minus over here. So this was another way I could write the equation. I'm going to construct my ice table based on the left one, but again, you can do it based on the right equation as well. They're essentially the same thing, because at the end, H3O plus, which is H3O plus, which is hydronium ion, is the same thing as H plus. So when you want to find the pH, you can just get the negative log of either one of them. All right, so here to do the ice table, I have to know the states because, for example, water is a liquid, so it's not going to be included in the ice table because it does not have concentration. But then these all have concentrations. Ions are always aqueous, and then the acid is aqueous as well. So then I can make my ice table. So initially, the concentration of acetic acid is given to us to be 1 molar. Since water is a liquid, we do not include it because it doesn't have concentration. The other two are always 0. Over time, this side becomes minus x. This is positive x, positive x. And then eventually, when you add up the two lines, this is going to be 1 minus x. This is going to be x and x. So if you recall, Ka is the K equilibrium of an acid. So it's essentially same as K equilibrium. And K equilibrium was always the concentration of products, which in this case CH is CH3COO minus, times the concentration of, times H3O plus, sorry, over the concentration of reactants, which would be the acetic acid. So Ka is given to us, and they should give it to you in order to find X. So in this case, 1.8 times 10 to the negative 5 is going to be equal to X times the other X, which is essentially X squared, over concentration of the reactant, which is 1 minus X. Now, for solving these, I can just do the regular calculation. So when I create the equation, it's going to be a quadratic equation because something is to the power of 2, X is to the power of 2, and then you have another X and all of that. So it's going to be a quadratic equation. But in chemistry, usually we can do assumptions to make some of the calculations easier. So this is one of those cases we can actually use assumption to make it easier for us to calculate X. And the assumption is that we can assume that the X in the denominator is so small that when you subtract it from 1, it does not change the value of 1. The reason we're making this assumption is because of the value of the Ka. Because our Ka is so small, that means it's a very weak acid. So the smaller this number is, the weaker your acid is. So because it's such a weak acid, the X, or the concentration of ions that we're making, is so little that when we subtract it from 1, it essentially doesn't change the value of 1 that much. So because of that, for simplicity, we can assume that the X in the denominator is negligible. So we should usually show our work for assumptions that we make. So here I can say the assumption is since Ka value is very small, so we're assuming that 1 minus x is essentially same as 1. And then once I do the calculation now, it's pretty much easy. It's much easier because now it's going to be 1.8 times 10 to the negative 5 times 1 is same as x squared. So x would be the square root of that. So x would end up becoming 4.2 times 10 to the negative 3. And X is essentially the concentration of both the products, which is hydronium ion and the acetate ion, but we're more interested about in concentration of hydronium ion. So because the question was asking for it. So now we have that concentration. Now, for the next part, it's asking us to find the pH of this solution. So pH, as you can see in the blue box on the left, is always found by getting the negative log of concentration of hydronium ion. So if I want to find the pH now, I can essentially just get the negative log of the concentration above, which is 4.2 times 10 to the negative 3. And my pH would end up becoming 2.38. So my pH is... can say it's 2.38, and that would be the pH of this weak acid. Okay, and another question they can ask you for a weak acid is to find the percent ionization of it, because as we said, a strong acid is the only one that ionizes 100%. A weak acid will definitely ionize less. So to find the percent ionization, we can use the formula that I wrote in the green box on the left. So percent ionization, as you can see, is always found by dividing the X, which is the concentration of the products or the change that we have, over the initial concentration, timesing it by 100. So in this case, our X was 4.2 times 10 to the negative 3 molar over our initial concentration was 1 molar. And then we times it by 100. So percent ionization ends up becoming 0.42%, which proves that this is a very weak acid. So this percentage is so low that it's not even 1%. So it's like such a low percentage of ionization, which proves that the acid is weak. Also keep in mind that when we're finding the percent ionization, it depends on both the X, the change that we get, and the initial. So if the initial concentration changes, the percent ionization would be slightly a different number. It's going to be around the same thing, but it will be a different number. Okay, so that was it for this video. I hope you enjoyed it. If you did, please make sure you like it. After this, I'm going to post my next video, which is about showing how to find the pH and pOH for a weak base. Hope to see you in the next one.